less time.
Thanks. And then it is my pleasure to announce the next talk. I was planning to have a brief announcement now in any case, because this next talk is a very special one, because Will Simmons has won the prize for the Best Student Paper Award. So let's do a virtual round of applause for him for that. There's lots of people clapping in the chat. I don't know if you can see that. So we're going to send you a beautiful poster, which I won't show now. So not a poster, a certificate. And your prize is that you have won a bottle from, which you can't see thanks to the virtual background, of the special version of the drink from the Selby and Sines Brewery, labelled mysteriously just by Bob. Or actually, we might make a Bob version 2 after we had a chat with Ross about this. So we'll see. We'll get that to you somehow. Anyway, Will, please share with us your award-winning talk.
Nice. Well, I wouldn't judge the talk just yet, but we'll give it a go. So thank you very much for the invitation to be here. It's pretty good fun. So the talk today is going to be on the circuit extraction problem from qubit NBQC. So we're trying to take measurement patterns and identify a unitary circuit that realizes the same linear map. So the particular motivation from my perspective on this was a couple of years ago in the world of circuit optimization and T-count reduction. We had these two papers that took very different methods, but ended up getting identical T-counts. So you had one paper by Kissinger and van der Wittering, who took circuits, represented them in the ZX calculus, and used rewrites inspired by rewrites on measurement patterns to reduce the representation down and identify places to merge gates. And on the other hand, you had this paper by Zhang and Chen, who represented the circuit as a sequence of rotations, explicitly abstracted away any Clifford actions to immediately identify the same set of rotation merges. So in trying to formally see whether these two were the same thing or not, mapping them, the actions in one representation to actions in the other, end up getting quite a number of results. So we came up with a simpler and slightly more general circuit extraction procedure compared to existing ones for universal measurement patterns. This extraction procedure relies on something called Pauli Flow, which is a generalization of causal flow and G-flow. So we had to also generalize the algorithms for identifying and focusing those and making sure everything still worked in reasonable time. We elaborated on the data structure used in that Zhang and Chen paper to incorporate other rewrites that allow it to simulate more things from the circuit optimization literature that go beyond what we're looking at here. And we ended up even proving some simulation results to show that the measurement-based rewrites, the effects that are happening on the circuit, can be simulated in this more circuit-like manner when we're just thinking about it as a sequence of rotations. So in this talk, for saving of time, we're just going to be focusing on the first one and getting in depth into the circuit extraction problem. I'm happy to take questions about the rest though, or come find me in Gather Town later today, happy to chat about it all. So we have this idea of a measurement pattern that we saw earlier from Robert's talk. And you can generally think, if you're not familiar with NBQC, you can think of a measurement pattern as a parameterized circuit of a specific form. So we often describe it by some labeled open graph. So we have some input qubits, and all other qubits are measured in the plus state. We then entangle each of our qubits with a CZ gate according to the edges of the graph. Then we go through and measure each of the qubits using single qubit measurements, leaving just some choice of output qubits. So we provide this parameterized circuit to the programmer, and the programmer specifies what measurements we want to apply on each qubit. So in which basis from the block sphere do we want to project it into? Now, we won't typically won't allow them to choose any arbitrary basis. We will often restrict it to some plane of the block sphere spanned by 2 Paulis, or in some cases even to a specific Pauli. So in that case, the programmer would either specify an angle within the plane, or simply do we want the positive outcome from the Pauli measurement or the negative one? So this, because these measurements are non-deterministic, we need some sort of corrections in the vein of the qubit teleportation algorithm to make an overall deterministic result. And the linear map we intend to implement through this is taken by our graph state, so the initialization of all of our non-input qubits, entangle them according to the graph, and then for every non-output qubit, we have the effect of post-selecting in the intended state defined by our measurement label, this lambda, and the programmed angle value, the alpha. So given a particular measurement pattern, or more generally just the labeled open graph, why do we know that these corrections work? And why do certain measurements have to happen before others? When can they be parallelized? So this all comes down to the idea of trying to give this characterization of when can we do this thing deterministically. And again, from the talk earlier today, the way to represent this is using a property called flow. So flow is equivalent to having stepwise determinism. That is, each measurement can be corrected individually on its own. And we specify a flow for this labeled graph by specifying a partial order over the measured vertices. So that is some ordering of our measurements. We make it a partial order to represent things that could happen in parallel, or at least measurements where we don't care which order they happen in. And for each qubit, we say, how do we correct it? So we do this by giving a stabilizer so stabilizer will just be a stabilizer of the graph state. So this is going to be a Pauli string, and it must flip the measurement outcome at our chosen vertex and leave all previous measurements unaffected. So we can think about it as we take this Pauli string of the stabilizer. When we experience the measurement error, so the unwanted outcome of each measurement, we can insert this stabilizer just by applying the equation, the Pauli over the measured vertex will flip the projector, giving us the same effect as the intended branch, and the rest is garbage over other qubits. But as long as we still have access to them, we can apply the inverse of that garbage to get the result we want. So the inverse of the garbage then becomes the corrections we apply. For this talk, the variant of flow we're looking at is called Pauli Flow. So we have both planar measurement angles, so being able to specify an arbitrary angle on the plane, and these specific Pauli measurement angles where the programmer is restricted. When you look into the literature on all of this, you'll often see the corrections defined in terms of a correcting set. This is taken from stuff on G-Flow. So a correcting set for a vertex V is some collection of vertices from which we can define this stabilizer. So we have an X for each qubit within the set, and a Z for each qubit within the odd neighborhood, up to some phase based on how we formed this. So what does it mean for this stabilizer to correct the measurement? Well, the component of this Pauli string at qubit V must be orthogonal to our measurement plane, so that it maps the negative outcome to the positive outcome. So for example, if our measurement plane is XY, take any point in the XY plane of the block sphere, apply a Z gate, you end up at the opposite point on the sphere. So we end up with the orthogonal state. And the condition for all of this stuff to be well ordered says any of these other qubits that receive some garbage from the stabilizer must be in the future of V, so they must not be measured yet. We must be able to still apply those corrections. The fun thing about Pauli Flow is we add an exception here. So we note that, let's say the expected correction on qubit W is going to be an X gate. Well, if qubit W is going to be measured in the X basis, that's not going, the X gate isn't going to change anything. So we might as well not do it. And in fact, this applies even if we've already measured W. So even if W is in the past of V, it won't have changed the projector applied. So we get this idea of some sort of free corrections that we don't have to do, or some people like to describe it as a limited correcting in the past, based on having these restricted Pauli measurements. Cool. So a very specific kind of flow called focus flow is what you get when you also impose the condition that we do this sort of implicit corrections as much as possible across the entire measurement pattern. So we say, whenever our qubit picks up garbage from a stabilizer, it must exactly match the measurement basis we're going to measure it in for these Pauli measurements. And now for the planar measurements, doesn't quite work out perfectly because, let's say, take an arbitrary point in the XY plane, it's going to be affected by any Pauli in some way. But given that X is at angle 0 in the XY plane and Z is at angle 0 in these other planes, based on how we define them, at least assigning it to be this way gives us the nice property that at angle 0, all of these corrections become implicit, they become free. So this means that, you know, when we end up with the majority of our measurement pattern being defined at angle 0, we have to do very, very few corrections, or at least can delay them further and further into the circuit. And surprising thing is that given any Pauli flow, we can adapt it to one that has this criteria. So we can always take a flow and give a focused flow back. Now, I'm going to add a definition here for a focused set, which is something like one of these correcting sets, but we're not correcting anything. It's just defining a stabilizer that satisfies this for all qubits. So it introduces garbage everywhere. The garbage goes away on measured qubits, leaving just something over the outputs. This is going to be important when we get to later parts of the extraction procedure. So came here to talk about extraction. So the general gist of the technique that I'm using is to say, I like stabilizer things. I like dealing with Cliffords. That's easy. It's nice and easy to compute with. So I really don't like these measurement angles being there. They introduce non-Clifford things. I want them gone. So I take the last measurement angle and try to find some simple unitary over the outputs that has the same effect as the change of basis of the measurement. And then I continue to work backwards through the rest of my measurement angles, extracting each of those in turn, until I'm left with something that is entirely Clifford and I can characterize by stabilizer methods. Cool. So the question is then, well, for starters, how can we move these measurement angles across? We do it using this handy little lemma here. This is not something that's novel, but it's extremely useful. If you remember one bit of maths from this talk, this is a good one to choose. If we have two commuting operators A and B, one is a stabilizer of some state or general linear map, then rotating around A has the same effect as rotating about the product AB. So how is this useful in our case? Well, measurement about an arbitrary angle in a plane is the same as rotating about that angle and then just doing a Pauli measurement. So we can take this rotation that gets applied to our graph state and change it according to some stabilizer of the graph state. So in particular, if we find some stabilizer such that this product PS is something only over our outputs, that gives us the form we want. It's also going to just be a rotation about a Pauli string. That's really easy to map down into a circuit using things like a rotation gate surrounded by ladders of C0s and some single qubit Cliffords. So we want to find a good stabilizer in this form. Well, we don't just have to use the graph state, we can use other things as well. So let's suppose we've got our graph state from the preparations and entanglements. We left in all of these Pauli measurements. We haven't removed the angles from them. We're just going to say those measurements have happened. And suppose we're partway through this extraction procedure. So we've already removed a few vertices from the future. So for any of these planar measurements in the future of V, we've projected them at angle 0. So we still want a stabilizer of this that matches that the rotation that's going to happen at V. So it needs to be a Pauli orthogonal to its measurement label. And otherwise, the stabilizer just needs to act over the outputs so that the residual is something completely moved. So the solution here is to use that focused Pauli flow we had. The fact that the Pauli flow corrects the measurement at V means that the component of the stabilizer there will be orthogonal. And in fact, for these planar ones, it will necessarily match this Pauli within that rotation. So it gets rid of it there. And the focused property means that all of the extra terms of the stabilizer on our other measured qubits will go away because we've got these zero angle projections or other Pauli projections. So all of those disappear and we end up with just the substring over the outputs. So this is easiest to look at with an example. So we have a small measurement pattern here with one input, two outputs. D is designated as a Pauli measurement here. So the last measurement we have to do according to our flow is going to be at C. So because we said, well, really the only things from our corrections that matter for the rotation are going to be the things happening over the outputs, we can just look at where the outputs occur in the correcting set and the odd neighborhood. So output 1 is in the correcting set, so it gets an X, and that's it. So the angle from C just implements a rotation about the string xi. Moving backwards, A and B can happen simultaneously. So let's just extract A first. We get an X at O2 and Z's at O1 and O2. So we end up with a rotation about the string ZY. Similarly, B has an X at O1, Z's at O1, O2. So we have a rotation around YZ. And finally, the rotation from I just has X at O2. So you can get the Pauli strings of these rotations just from looking at your corrections. The phases of them have simple functions to define based off of the measurement label and the other contents within these sets, but they're relatively simple to calculate. Cool. So now that we've found a way to get rid of all of those measurement angles, we're left with something that's Clifford. So we can characterize it, for example, by a stabilizer tableau. So depending on where you're familiar with stabilizer tableaus from, you may think of them as applying to states, or you may think of them as applying to unit trees. And in general here, we're going to have an isometry. We'll have some number of inputs that will just be less than the number of outputs. So we need to slightly generalize them here. You can fix this by, say, representing our isometry by its Choi matrix and using the state tableau of that. Or you can use what I do, which is we take the unitary representation, which defines the actions of the Clifford process on Z and I for each input. And then additionally, we provide some extra stabilizer generators over the outputs. This just gives us a little bit more structure to help identify these than just using the Choi matrix version, but they're isomorphic, again, up to this, just using the Choi isomorphism. So, okay, this tells us what we need to characterize it. How do we go about finding these things? So what about these actions? Well, you can get those from the Pauli flow as well. Let's say we take a Z, stick it on an input. The Z will commute through any CZs in our for generating the graph state. And there's a general rule where in Pauli flow, your inputs, in order to be deterministically corrected, must be measured in the XY plane. So they must be corrected by a Z. This means that the correction from the Pauli flow will negate that Z and present us something just over the outputs because of the focus condition. So again, we can just read off the at least the Pauli string for this row just from the corrections over the outputs. For the X, we have to do a little bit further. So we take the idea of an input extension. So an input extension is where we take our measurement pattern. We add an extra qubit that is attached just to our input, and we make that the new input. This changes the linear map we're representing up to adding a Hadamard at the front. So because we're adding a Hadamard, the Z action of this input extension is going to be the same as the X action of our original measurement pattern. So by taking an input extension and similarly using a focused Pauli flow for that, we can identify the X action. Okay, so what about these additional generators over the outputs? How do we find them? Well, you remember I talked about those focus sets earlier, the things which just generate garbage over the outputs. We want those here. They give us exactly what we want because we projected out all the rest. And there is an efficient algorithm for identifying generators of the group of focus sets, and thus we get generators for this subgroup of stabilizers. So again, if we look at our example here, for the Z action, we can just look at the corrections of the input. So we just get X at 2. For the X action, we can say, well, we can kind of cheat a bit. This itself is an input extension of the graph excluding I with the input at B. So because that would be, we take out a Hadamard at the front, that has the same effect as adding a Hadamard at the front. So we can just look at the row for B and see that, again, our X action will be Y, Z. And we get a focus set that has the output 2 in the set and output 1 in the odd neighborhood. So we get a stabilizer ZX. So kind of summarizing where we've got to, we will be pretty much at the end with this. We've managed to rewrite our linear map in terms of a Clifford isometry and a Pauli rotation for each one of our planar measurement angles. Each of these is easy to synthesize into circuits, and this map exactly matches, or up to some very basic rewriting, the representation from that the Zhang and Chen paper I mentioned earlier, this data structure used for circuit level rewriting, that just abstracts away Clifford stuff. Cool. There are some neat things that came out of Lemmas when doing all of this. Things like focused Pauli flows are unique when we're dealing with the unitary case, and the fact that the causal order from between your measurements is exactly the order of dependencies between the rotations that happen at the circuit level. So where we can no longer commute rotations past one another. So there's no causal order things that mean we can get big improvements going to MBQC and back, or vice versa. that it's really preserving any sort of causal structure there. So summarize, made it much easier to see the impact of each measurement angle given a flow, because you can just look at the corrections on the outputs and say, oh, we're rotating about that Pauli string in some direction. And we can use this to prove simulation results about rewrites in MBQC, and potentially future work might use this to compare algorithms between MBQC and circuit language. Like, I'd quite like this to formalize some relationship between measurement-based VQE and adapt VQE to show that they are, again, the same damn thing. Cool. Cheers.